Presentation today is microgrids, out with the new and in with the old. Practiced that several times and got it right, which is good. So again, my name's Alex Schmidt. I'm distribution team lead for HDR, PE in Illinois and Wisconsin. I got my bachelor's at Bradley University in Peoria, Illinois, and my MBA from Western Illinois, obviously in Illinois. So move on from that. Enough intro about me. Completion requirements here. So this course is a PDH. So all we ask is you attend the entire session and you have active participation. We'll have a time for Q&A at the end here. So that can be that active participation. Really, that just means, don't fall asleep. Don't be doing the dishes. We're here to learn. So copyright materials. So this is copyright protected. It's HDR property, but as I go through here today, I do have my references in the notes. So if you see something that you want to see what the reference is or whatever, I can certainly send you this presentation, no big deal. But just have to put that in there for legal reasons. So we're going to start off today with the problem statement, microgrids, the why, right? So why are, kind of like sustainability, why is this becoming such a hot topic that we're hearing in the industry? And the answer to that really is the grid stability and resiliency is declining, and we need a way to adapt to it. So the learning objectives today, understanding the basic concepts of microgrids. We're not going to go into crazy protection schemes or anything like that. It's just kind of a high overview. Understand why resiliency on the electrical grid is becoming such an important topic, and learn why going green and microgrids are really intertwined. You can't really have one without the other in an effective manner. And then my favorite part is just being excited about the future. I think all of us are extremely busy in this industry right now, especially, and it's easy to lose sight of why we go to work. And I think one of the simple reasons is we're in a cool time right now. So to get excited is kind of my main goal of today. So grid definitions and history. So what is the grid? And I'm going to read straight from this just because it's a long definition, but this is from the EPA straight off their website. So a complex machine in which electricity is generated at centralized power plants and decentralized units and is transported through a system, substations, transformers, transmission lines, and distribution lines that deliver the product to its end user, the consumer. Since large amounts of electricity cannot be stored, it must be produced as it's used. And I think that last sentence there is really the takeaway from what we're going to define as the traditional grid. It's on-demand energy supply from large units. And then, so what is a microgrid? And again, this one's from the DOE, but a group of interconnected loads and distributed energy resources within clearly defined electrical boundaries that acts as a single controlled entity with respect to the grid and can connect and disconnect from the grid to enable it to operate in both grid connected or island mode. And hopefully your takeaway there is that sounds a lot more complicated, because that's the point. It's a lot of inner working parts to make a microgrid and many microgrids across the grid itself. So a little bit of history of the grid. So in 1839, I found this fascinating. The first photovoltaic effect was witnessed by Edmund Barkell. And that's almost 200 years ago, which is crazy when solar is just getting ramped up today. And then so 1882, first microgrid was created. I'm terming this the first microgrid because it was kind of the start of the grid by Thomas Edison. The Pearl Street station was a coal-fired steam engine 1.1 megawatts of DC power. And if you're in the power industry, you'll think, wow, 1.1 megawatts is nothing. We have diesel generators that are multiples of that, and then DC power, which is it's another interesting concept. We're typically using AC. And then in 87, the first wind turbine in Scotland, which is also crazy to think, that's 40 years after the photovoltaic effect was observed. And then first nuclear reactor at the Ebre in 1951. So a big gap there and kind of the technology jump. But if you know anything, the 50s, 60s, and 70s were the nuclear time. So today's grid, the U.S. grid. So on the left is kind of a simple diagram. So we'll just kind of walk through what that grid is. So you have a power plant. You need some type of generation. That's going to go to a transmission substation. So we're going to increase the voltage so we can get that voltage across really long distances. Then we're going to go to another substation where we're going to lower that voltage, put that on distribution lines. So if you see those power poles, that's your distribution lines. And then we're going to go to what you could call another substation. It's just a pole mount transformer, but that's going to drop the voltage even further. So it's usable for a house or a business, what have you, because we don't need to transmit very far once we get to that point. So, and then on the right we have kind of a more complicated diagram, but you can see we're tying through high voltage, very large generation assets, hydro dams, coal plants, nukes. Then we're going across a lot of distance. Then maybe we have some kind of mid-range generation assets at a more lower end, higher voltage, I'll say. And then we're going down to distribution, and we can still have generation assets on distribution. They just might be a little bit smaller, maybe 50 megawatts or something like that. And we're also going to have our loads on that point as well. It might be an industrial that we bring in medium voltage power to. It might just be a residential customer that we have a bunch of pole top transformers. But yeah, so you can see it can be quite complicated with all the customers. So this is just a cool graph of the transmission grid right now. Just thought it was interesting. You can see too, there's gray in there. It's 115 kV kilovolts. So it's pretty, kind of just keeps growing the more you look at it, but it just shows how much transmission's out there, and we have a lot more going up. So pretty cool. So this is just a little for you non-electricals, maybe we'll reason on why our grid is the way it is. So this is a example of Ohm's law. So we go from our power plant, like we were talking about, to a substation, increase the voltage, right? So on the top half, we're going to increase that voltage to 1 kV or 110 kV. And on the bottom one, we're going to increase it to 220. They're going to be the same power because the equation for power is power equals current times voltage. So you can see they're kind of just kind of inverses per se, but still the same power if we follow that equation. So we're going to transmit the same power with the same resistance across to our substation that brings down the voltage. So we'll bring it in this instance for 220 volts, so same voltage, but you'll notice that the 220 kV had 99.99 amps transmitted, but the 110 had that 0.96, meaning that we had higher losses at that 110 kV than we did at that 220 kV. So it's just kind of an easy example of why we go to that high voltage, because it's really easy to think, wow, why do we spend so much money on on these giant transmission poles? That seems ridiculous, but there's good reason. You need to spend a lot more on copper. So the evolution of microgrids. So microgrids now contain assets which are controlled continuously, utility tied, parallel operation. So you can't have the utility controlling your generation assets on the grid. We can use any energy source, so whether it be solar, wind, what have you, with with the microgrids, it's very easy for them to implement those assets. And then you can have typically two modes of operation, grid tied and island. I'll talk about those a little bit later, but just some examples here too of all the different assets you can use on a microgrid: battery storage, wind, waste energy, etc. So the changes requiring microgrids, electrification demand is rising. So we got heat pumps. I'm sure you've heard those in the news quite often. Electric vehicles, DERs, distributed energy resources. So those are things like solar, wind, energy storage, anything that's not your typical generation. And then need for resiliency. So whether it be just communities or the military, everyone wants their energy and they don't want it to go down. And so we need to consider that resiliency. So some new technologies for the future. So microgrid technologies, we can have anything from combustion turbines, reciprocating engines, heat pumps, solar, wind, battery storage, EVs, fuel cells, and then combined heat and power, which you'll see talk about a little later, but it's CHP is typically what you'll hear. But the key thing here to me is we have such a broad gamut now of the size that we can generate at. So, I mean, this little chart on the bottom here says 1 kilowatt to 50 megawatts, but I mean, they make solar panels you can stick on your apartment balcony and plug it into an outlet. So there's really a infinite amount of generation assets you can use, even consumers. So electrification projections. So this one on the left here, I believe, was created in 2023. So it goes back a ways and then goes up to 2026. But this is the EV projections. So you can see during that 2020 era, it was pretty exponential, and now it's fairly linear as far as vehicles sold. But I think that shows that each year we're steadily increasing in EVs, and that demand is steadily increasing. And I think it's only going to continue, and so we're going to need to consider those loads for the grid as these high demand loads increase as far as vehicles. And then on the right there, it just shows this was a 2022 report that showed the 64.8 billion market for heat pumps, going up to 142 is the analyst projections by 2030. So, I mean, that's over, it's about 2.5 times the increase there over that 8 years. So we're only going to see more funds being put to heat pumps as that market of electrification continues. So two things to watch for, I think, just because these loads are really going to affect the grid. We're going to need to increase our transmission and distribution lines. It's going to be a lot of money to support this new way of having energy. So some DER projections. So all I could find for this was a 2021 graph, but it's pretty good. So this was in 2021, they went from the 4% solar to 22% projection by 2050. I think that's probably accurate. And then 9% to 14 on wind. That's probably good. Then 6% to 5% on hydro. I wouldn't say we're super landlocked on hydro, but it's a big cost on hydro, so I think that'll probably stay steady. And then the 37 to 34 on natural gas. Natural gas is considered pretty clean. Like, it burns pretty clean. You don't need after treatment as bad as diesel, but obviously there's a fracking issue. And then nuclear, they're showing that to go down. I disagree with that, but it's an interesting perspective. And then coal, obviously, that's going the way of the dinosaur, pun intended, I guess, on that one. So power generation market. So this was a 2023 projection. They didn't have a 2024 produced, unfortunately. But this just shows you this is how much generation assets were going to be produced for 2023. in the US here. So 54% solar, like that's crazy, right? And then 17% battery energy storage. So at that point, you're at 70% what we would call renewables, right? Um, that's I don't know, that gets me excited to work on this stuff. And then you got another 11% wind, so that's 80%, right? We're definitely heading in the right direction. We have an uphill battle in the fact that we have to we have our loads growing at the same time we're trying to change over a ton of old assets. But if this gives you, or if anything gives you hope, I think figures like this hopefully do. So how microgrids work. And I think I don't have my notes here because I'm just sharing the presentation directly on my screen. But I think this might have been one of the AI, Adobe AI generated pictures. There's another cool one too. So I just thought that was kind of fun since we're kind of talking about new technology, marketing, use some AI, licensed AI, I should say, for this presentation. So going to talk about just a quick diagram. So on the left here, this is kind of a grid tied model. And then on the right here, this would be your islanding model. So on the left, say you have a turbine and solar panels on your microgrid, and you have loads that are on your site or whatever hospital. So in this case, you would be doing what it would be called line interactive. Basically, your solar panels and turbine would be syncing to the utility, and because it's a 60 hertz AC waveform, so you would sync to that 60 hertz waveform, and then be able to push current into that grid. So if your loads were less than your generation, you would actually, that's when you push back into the utility. That's why it's so important to have a utility interconnect agreement. And then if they were greater than that, you would just be, the utility would supply the difference. And then on the right is your islanding mode. So basically you just, flick a light switch, right? You disconnect from the grid. And as long as your generation is bigger than your loads, you'll be fine. Otherwise, you might need to load shed a little bit. But so those are the two when you hear islanding and grid tied. Those are kind of what they're talking about. So microgrid's a concept not so new. So I think the term can kind of seem scary sometimes when it's maybe it's not in your industry and it's all this new technology. But I worked in healthcare for 6 years, and every hospital I've ever worked at was a microgrid, right? So they have generators, and they have to be able to supply their emergency wings and all that. So they disconnect their power and can sustain themselves most time indefinitely because they have agreements to get diesel on site fairly quickly. So they would just keep shipping in more diesel. But so you've seen them, and then like DoD bases, they have on-site generation. So they're already there. We're just kind of improving and making it more sustainable, I guess. So I have one, and you probably do too. So this is my, which I'm very proud of, my new, as of 6 months ago, generator. Kicked the old one out. But this is just a generator that I roll outside, plug it into the outlet that's designated for it, switch over my transfer switch, and then that power then flows into the circuits that are designated. And I have myself a little microgrid, keeping my refrigerator and some lights on and stuff like that, right? So this is just meant to show you that it's not scary. It can be as simple as a generator and a panel, and there you go, you have power. So the nerdy stuff, this is my favorite part. So CHP, so why it's so cool is I put a little picture of a car exhaust here on the left, but if you have generation, you have losses in the form of heat, whether it be combustion heat, friction from your oils and pistons. But anyway, you have losses that are just thrown out to atmosphere. So the idea behind CHP is, why don't we do something with those losses? So basically, you take the exhaust gases and you do something with them, right? And you can run that through a heat exchanger. and you can take that heat and heat dorms if you have a school or whatever. So you can instead of just throwing that outside, you take that heat and do something with it, and then you still have that generation from the electricity through your engines to use to the grid and your campus or whatever. But it's a very simple concept, but I think it's very smart. It's very efficient. Because and engines are only like 35% efficient, which always blows my mind as a figure that I learned in physics in high school. So that means 65% is going out the tailpipe, which is nuts. So SMRs. So this is one person at HDR told me that we should be excited because we're living in the nuclear revolution, which is also why I don't believe those figures about nuclear going down. So SMRs are basically small modular reactors. Basically, you create a reactor and you factory build all these components, and instead of stick building it, you can build it in kind of like Legos. So there you have all the benefits of factory creation, right? If you've ever, I don't know, I think about when I build stuff myself and it works, but it looks homemade, and then I buy something, that was from a factory and it looks amazing. You get all those benefits if you build something in a factory than just stick building it. So better quality, higher resiliency because you have better quality control in the factory, less voltage drop because you can put, you put more of them throughout the area as opposed to just having one in the middle of nowhere and then having to transmit that power into a city or whatever. You can they're only about a football field big. So that's not, if you've ever seen a nuke plant, it's very small relative to a normal nuke. So really, really cool concept. And I know a lot of people say, are they safe? But USS Nautilus was the first nuke submarine. And these people are living in a submarine that is powered by nuclear energy, and they're living right next to that nuclear energy. So I don't know. Nothing else that should give you some confidence. Certainly does for me. And then radiation, I think when people talk about radiation, they talk about it like it's a bad thing, but currently in the room I'm sitting in, there's sunlight coming in, there's radiation, right? If your lights are on, that's visible radiation. Radio waves are everywhere. The radiation you have to be scared of is that what we call high energy radiation. So kind of on the left there, you see that X-ray and gamma ray radiation. That's the stuff that you've probably heard, right? That's bad. The reason it's so radiation can be blocked like microwaves. The reason you have like in your microwave those little holes, it's actually because as long as those are significantly smaller, I think it's a quarter, but microwaves are actually, those holes are 100 times smaller than the microwave itself, the wavelength. So as long as those are smaller than the wavelength, it appears as just a black wall, like the radiation cannot permeate it, so it just bounces around in there. So that's why the radio waves and stuff, they'll get blocked by buildings because the radio waves are massively long, and even those buildings there's gaps. It's still way smaller than the radio wave. So it's key to understand that radiation's everywhere, and we just have to be careful with certain types. Heat pumps. So heat pumps, again, I think another one that's maybe overly complicated. I think they're super awesome, but they're not scary. All they are is you have your typical air conditioner that you have in your house, right? And so your evaporator's outside, your condenser's inside. All it does is flip the refrigerant flow. So then effectively you flip the evaporator and condenser. And so now the hot thing is inside and the cold thing is outside. And you're just moving heat energy. And so you can kind of think of it, like so the reason it works is because the evaporation is a factor of latent heat. So I should probably move to this slide there. There we go, latent heat. So latent heat, if you remember from Physics 101 in college, the latent heat is the heat required or the energy to transition from a one phase to another. So it's a phase change heat, basically. So when you sweat at the gym, basically, the liquid that's on your skin, the reason you perspire actually is because your body is taking advantage of latent heat. So you'll notice, like, you'll go for a run, you'll start sweating, you'll get hot, and then you stop running, and then all of a sudden you're like, wow, I'm starting to feel kind of cold. It's because that evaporation's happening, and as that phase change happens, that gas takes with it a disproportional amount of heat energy to transition to gas. So that's what heat pumps are doing, is they keep going back and forth with heat, cooling and heating in this refrigeration cycle. And so they're using the latent heat physical property. So I don't know, pretty cool, right? So solar panels. This is kind of a easier version, but it's a cool infograph. So basically, you have a photon, right? Photons are light. They knock a electron free in the silicon, and then those can move around. So they move around in a DC current. And then that goes to your inverter. The inverter is the thing that makes the sinusoidal wave, so 60 hertz here in the US. And then that goes to the grid, and it can sync with the grid, or whatever other technologies are on that inverter. But that's the basics of how it works. One cool thing too is perovskite technology. So it's not necessarily new, but I think we're getting close to perovskites being feasible in solar panel creation. So it's just another rock on the ground or whatever, but it has a property to be able to absorb another wavelength aside from silicon. So what they're doing is we can get a wider spectrum of absorption if we use perovskite and silicon. And so one manufacturer, I think they're going to come to market in like 2 years, I think they were saying. But what we're seeing from them, at least early on, which we'll see if this happens, but 30% efficiency, and if you're in the market right now, you'll see about 23.5% efficiency, depending on the binning. So if we can get a 25% reduction in solar panels and have the same output, that's going to be great for everyone, for landowners and manufacturers making it. There's just some long-term things they're working through. They typically don't last very long, but I think they're able to mix in some other things to shield the perovskites from degradation. So pretty cool stuff. Should look it up when you get a chance. The duck curve. This is the bane of any solar designer's existence, and probably all the utility folks on here. So what this is this is a load curve. If you have solar on your grid, so your microgrid, your standard grid. But basically, you can imagine that, say, around 12 to 3, it's roughly the sweet spot in there for when the sun's blasting the solar panels. So that's going to take that load down because the solar panels are increasing during that time. But then what happens is, you may have businesses shut down, but everyone comes home, turns on their stove, their AC, plugs on their EV car, and your solar's now going down around the 6 o'clock time when the sun's going down, right? So we're seeing this peak, and I forget who it was who coined the duck curve, but you can see why they call it a duck curve. There's a little ducky in the background there. So it's something that I think battery energy storage is going to help us with, because at a certain point you'll get so much solar that during 2 o'clock you're not you don't have enough load to support it, and then 6 o'clock you're up a creek. So wind. So when there was a certain person I was talking to at a certain utility here in Wisconsin at a conference, and he was like, yeah, we helped with the maximum wind turbine legislation, and then a couple years later we had to turn around and say, actually, we need to go higher, right? And these things keep getting higher, and the simple reason is we need to get the blades longer, because of area, right? So pi r squared. So the longer you can get the blades, the more area you cover. And I think this graph shows it pretty well. So you can significantly increase your output. The more area you can pick up, and the higher you can get them up there. And there's some wind stream things in that with that. But so we're just seeing those increase over and over again. And I think we're going to see more and more useful wind energy. So the problem here, kind of like the duck curve, though, is wind intermittency. You're going to have days that there's no wind. You're going to have days that you're blowing it through the roof. And you can kind of see that on this chart here this is just 2020, but it gets the point across, right? Like, what do you do during those days that you have nothing? And then compared to those days, you have a ton of wind, right? So it's definitely a problem that we're going to see over and over again with renewables, and that's where any type of storage, I don't want to just say battery, but any type of storage can help smooth this curve and make it all feasible. So EVs. I know some of us are probably sick of hearing about them, but they are important. And so I do think we need to talk about them. So what's the whole point of why we're talking about EVs is they can be used as renewables, right? They're not just a load, they're a generation asset. I like that sheep out there too under the solar panels. But so I think it's important to keep talking about them because I think there's more potential than we're discussing. So here's just a cute little infograph, right? So during the night, we discharge this battery down. So during the day, we can plug it in and increase it. So maybe what this looks like is you charge your car at work, right? Maybe I know at my current office we actually have free charging, and then you allow the company to discharge during the night and use your energy. I'm sure they'll start charging here soon once everyone hears that and thinks about that. But it's certainly important. And some folks, a lot of school districts have actually talked about their school buses. And you got a summer of them just sitting there during high loads. Why can't we just use school buses as energy storage? And it's certainly extremely viable option as opposed to just your standard bus that 90% of them are sitting there over the summer. So battery technologies, I think a lot of people get, there's a lot of negativity around like, well, EVs will never be, whatever, batteries aren't good, whatever. But I remember, 30 years ago when I was a kid, my dad had a DeWalt hand drill, and that thing lasted a year. And then the battery, you'd get 10 screws in and you'd have to charge the battery. I think it was a NiCad type battery, but now I've switched to Team Red, so I'm a Milwaukee guy now, but we have lithium ion batteries that I've had those things forever and they still hold a great charge. And I never have to charge them, maybe once every few projects. So the lithium ions come a long way, and there's so many different things that we can talk about as far as like why we're going to progress battery technology. But I think this chart here just kind of shows, we're slowly increasing the volumetric and gravimetric density, which is what we want to do. We want to travel along this line here that we're seeing. And then cost, right? Like I bought a battery for my Subaru. I have a refrigerator in my car, and I think that price I bought that 3 years ago, and that price has come down already like 30%. So, and especially here on this chart, right, like 2013 to 2022, 80% drop or whatever that is. That's crazy. So we're only going to see that cost decrease, and that's only going to make EVs more and battery storage more viable, right? So I think that's exciting. And then some different technologies. I'm sure some of us have heard a lot about solid state and maybe are still holding our breath, but there's manufacturers still touting that it's coming, and it's super cool because the concept isn't crazy or anything. So in a battery, you have an anode cathode, right? The negative and positive parts. and you have an electrolyte that just allows those electrons to flow between the two. So if you can have a solid electrolyte, you can combine all those and you don't have to have them in separate cells into a smaller form factor. So you don't have all that liquid electrolyte floating around on the outsides. And really, I think it's like 30% more energy you gain just from changing to solid state. Might be more than that, but it's crazy. And then you get faster charging, longer life. They're talking thermal stability. There's a lot of cool benefits that I think we're going to see here shortly with solid state technology. So super exciting. So grid stability and resiliency. This was definitely AI generated. So that's number 2. As it was stated, I worked on a lot of microgrid stuff for the federal government. And so Executive Order 14057, catalyzing clean energy industries and jobs through federal sustainability. You got to wonder where they come up with these names. But so by 65% by 2030, that's interesting and difficult, but it just shows the commitment that people want to go towards, shoot for the stars, land on the moon, right? And then net zero emissions by 2050. That's ideal. But again, anyway, 100% zero emissions vehicle acquisition that's light duty vehicle by 2027. And then 100% for all vehicles, so medium duty and heavy duty by 2035. So GSA is already the body that buys vehicles for the government. They're obviously looking at that stuff. But I think it's just interesting to see, like, all hands on deck. We need to work towards this. And so resiliency is key. So resiliency, the power ability to return to the original operating condition after loss of power, natural disaster, etc. So you have your ride through. That's the time that you can continue without a utilities assistance. It depends on your loads, how much generation you have. And then, you might look at a load shedding scheme. So, hey, in my case, I don't need the kitchen lights on. I want the refrigerator to stay on. So maybe I go and turn the breaker off for the kitchen lights, right? If I start running out of gasoline. Stop and recover. So what's called a black start. So basically just starting from nothing. So what's your recovery time? Some of these generators can take, a minute to start up. If you're talking like large generation, you're talking a lot longer than that. But, a small 2.5 meg, you could start that up in a minute for natural gas or diesel. But is that quick enough? How long? And then, do you reclose? So, do you automatically connect back to the grid, or, what are those schemes? So there's a lot to consider there. So some of the challenges. So grid tie versus island, we talked about that, right? You have to make that decision. Grid tie is certainly more complicated. Voltage sync. So kind of going back to the grid tie is you're going to have to sync up with that utilities voltage. And it's not necessarily easy. We just buy the equipment and install it, but there's programmers that spend a lot of time on that. Grid failure, so how you're going to deal with it if the utility goes out, utility coordination, interconnection agreements, procurement, maintenance, like all that's on you if you own a microgrid. So grid tie-ins. So this is just a little diagram of all the stuff that's going on in the grid, and it's a lot, right? So protection schemes, which I mentioned a little bit in that couple slides ago, but there's the utility. They have these overcurrent protection or however their protection scheme's running, right? There's a lot of different types, but they have these set, and so then you add in some guy who wants to generate his own 10 megawatts, and so now it's just another complexity that they have to interface with for protection, for making sure that they can keep as many customers up as possible if there's a fault, right? So it just adds all these levels of complexity. And I think sometimes people probably don't appreciate like that all these things are going on in the background that keep your power on. And so on the right here, I just think it's kind of crazy. This is probably low voltage diagram, but like all these motors and loads are all in different zones of protection, and there's just a lot going on. So it's just something to contend with. That's an engineering challenge. And then many entities, right? So you got your wind farm. Your Joe just bought his new house with solar panels, the hospital down the road, and then the new SMR that's going up by 2040. But just a lot of people to coordinate with. So summary. This was also this is my favorite AI generated photo. But so distributed generation market drivers. So resilience. So we got to keep the government and hospitals working. So they want to, as things become electrified, they want to take that generation into their own hands, right? They don't want to have someone, whatever, a foreign body bomb a substation, and now the utility, they're out for 2 weeks. They want to be able to maintain their resiliency. Costs are going down for sure. So as costs go down, right, demand's going to go up for that equipment. And then sustainability, I think, maybe I'm a glass half full guy, but I like to think that's the main driver. It's really what excites me is knowing that we're all working towards something that we think is going to sustain this earth, that we only have one of. So I hope that's the takeaway here, but whatever works for you. So yesterday's grid, just centralized generation with a bunch of loads, right? And then tomorrow's grid, more complex for sure, but a lot of distributed generation assets, more smaller assets scattered throughout the loads, and I think it's more complex for sure, but it's going to get us to that sustainability goal, and those resiliency goals too. So with that, my name is Alex Schmidt. You can reach me at my email or phone number down there. That's my LinkedIn QR code for the savvy folks. But yeah, I'll guess from here we open it up to questions.
Thanks, Alex. That was great. What do you think about battery storage for like solar applications and just where the technology's at right now?
Yeah, I think right now, I mean, we're certainly doing a lot of battery storage, and I think if there's enough money, certainly it's a good option, but I think it's still early as far as its capacity. There's actually, so I live in Columbia County, Wisconsin, and they're doing a new, it's the test version of a giant CO2 dome. So basically they're going to pump CO2 into this thing, compress it a little bit, and allow it to, run it back through the other way, and that'll be the energy produced. So it's like 10 megawatts. I don't know how many megawatt hours it is, but it's going to be a giant. I call it the pillow. It's going to look like a giant white pillow. So I think there's other ways to store energy that we can also look at. But as far as like density goes, battery energy storage is probably the best. So if you only have a certain amount of land, it's probably the best option for now. But there's also like there's heat storage. So like you can store heat in these, I forget the name of the company, but they're giant tubes of sand, and you pump the heat into the sand, and sand is really good at holding energy. So point being, there's a ton of options. I think batteries still have a ways to come. Not that you shouldn't keep buying batteries out there and have us do projects for you, for those folks out there who are thinking about it. But I do think it has a ways to come, and I think it'll get there, and I think solar or solid state is going to be a big driver to that. Yeah, I don't know. It's exciting.
Thanks.
Oh, come on, active participation.
Alex, how many SMRs are currently being built in North America? Or
Oh.
just rough numbers?
I don't I'm glad someone tripped me up. I was hoping to be. I don't have that one offhand. I think from what I understand, North America is lacking in SMRs. But like Europe and that area, they're financing quite a lot. I think that's where Westinghouse and all those folks are getting a lot of their revenue from. Just because I think the legislature out there, is a little bit more driven to almost force that issue. And I also think Americans probably have a little bit of a, we've had some at-home issues with nuclear. So I think Americans still have a little bit of a way to go as far as like the view of nuclear. So I'm hoping to change that with just, voicing my opinion everywhere. But I don't know how many in North America are being built. I don't even know if there are any in North America being built, but I know there are a good handful in Europe being purchased and built. So sorry for the non-answer, but that's what I know. Rami has a question.
Oh, yes. Thank you so much, Alex, for the information that you have provided. I have a question. What we, as we go toward the recent technology, like and the complexity of the grid, um, how that is going to be affected with the, I would say, yeah, we're going for resilience, but what about uh, the environmental issue here in North America? Which of these systems can sustain any heavy storms and like restoring power again and all these things that we face, um, and how that can be easy, like I would say how the system can be easily affected, or the newer grids, how they uh, be easily affected with that, or how can they sustain storms and other things like that?
Yeah. So it's definitely a good question. So like climate change, where is an issue, right? But I was watching something over the weekend and they said the 100-year rain event is now the 33-year rain event. So um, it's definitely a major issue. I think I think eh, diversifying our generation is the key. And to me, it's ignorant to think that we'll never have a base load of a diesel generator, something like that. At least not in the near term, next 50, 75 years. So I think we're always going to need those backups. But, if we can have some type of storage, whether it's battery or pump hydro or whatever, um, and 80% of our generation is based on it is based on renewables, so solar, wind, and there's more being talked about every day, different types of renewables. But I think that storage aspect is really going to be the key for what I'll call renewables resiliency. Um, but on the flip side, I think it's ignorant to think, okay, we need to get rid of all reciprocating engines or turbines or whatever. I think those make a great baseload and a great backup for emergencies. And I'm talking grid scale, not just like my little home generator. I think those make a great backup for emergencies, especially. So I think, we didn't start having these problems till we, had 7 billion people on the world and had all this energy demand. So if we can drop our base load to 20% of petroleum and then 80% renewables, I think that'll probably, we'll balance that need for resiliency and having those petroleum assets offline and for emergencies. But most of our generation will come from renewables. But I think it's a good question, and I think it's hard to answer what the future will hold. I mean, I just had a year where I only went snowboarding 3 times, so it's kind of crazy. So it's hard to say, but I think diversifying generation assets is probably my answer. We have 4
Alex,
minutes.
There's a couple of questions in the chat.
Oh, geez.
Good, Matt.
Nuclear is going down as plants age out and permitting makes new reactors hard to create. Yeah, I do think, though, I think there's a shift. I hope maybe it's optimism. We'll see. A few of our biggest obstacles for conventional nuclear reactors are high capital costs, lower ROI, environmental backlash. Absolutely. Molten salt. Yeah, so that's kind of the similar thing of storing heat energy. There's a lot of different ways you can do it. There's even like ones that are pumping heat and they'll shine a bunch of mirrors at them to a single point, and then they'll pump water through it and then put that into some dense energy storage. What are the thoughts on community scale microgrids compared to utility funded? I actually like that. I actually recently thought about doing that with my HOA and proposing that on the plot of land that's empty. I think it's just hard to get a group of people who may or may not know, be engineers to collaborate on that. If you have a driver doing it, I think it's easier, but it's just hard, right? There's a lot of governmental agencies that are in the way of certain things. So in Arizona, it's like just about every house has solar panels. That makes sense. In Wisconsin, is it really worth it from a cost benefit? Still seems like it's hard to sell for me. Again, I love to do solar, but it doesn't make sense on your house in Wisconsin. No, I mean, there is an ROI. It's just a long time, and like, there's so many different things. Like, you can get into the construction of when you replace your roof and Elon Musk's roof panels and all this. But for me personally, I don't remember what the ROI was offhand. I want to say it was like 15 years, but it doesn't make sense just because it's such a heavy investment. But yeah, certainly in Arizona, it's once you get kind of midpoint or south on the US, it starts to make a whole lot of sense, and it's really cool. I have to take off. Thank you. So yeah, there we go. Cool. All right, looks like we're right about at time, so I want to be respectful of everyone. Again, if you have any questions or you just want to chat, give me a ring. Happy to chat. If you don't have my contact info, Andrew can send it to you. We got one more question from Ian. Ian, did you want to say something? Probably got 30 seconds. All right, I'm assuming that was a wave instead of a hands up. So, Andrew, I think we're all good.